All right, so I want to just cover really quickly. This actually is a review lesson for most of you. And just want to talk about higher derivatives, section 2.8 in your calculus text. Higher derivatives, we're talking about the second derivative, the third derivative, and so on. Okay, fourth derivative, and so on. So this right here, actually, you might see this fourth derivative. You might see them start to write it like this with a kind of a bracket forming the fourth derivative. But anyways, we won't worry too much about that. First derivatives, second, third derivatives are kind of what we're focusing on. So the higher derivatives, if you want to find a second derivative, okay, first of all, this notation is the exact same as this notation, means the same thing. And the second derivative in Leibniz notation is the derivative of the first derivative, which turns out to be this, okay? Now you'll hear this referred to different ways, d2y over dx squared. You'll hear it d squared y over dx squared. This is the second derivative, so the 2 is here and the 2 is here. For higher derivatives than this, you'd have a 3 here and a 3 here for the third derivative, let's say. Now, the concept is really simple. You know how to take the first derivative, and that's all you need to know for this section. To find the second derivative, you calculate the first derivative, and for this example right here, for y equals x to the fourth plus 6x squared, the first derivative looks like this, and the second derivative is simply the derivative of the derivative. And so you get a second derivative that looks like this. If you wanted to find the third derivative, you would take the derivative of the second derivative. You see what's happening? So that's what higher derivatives mean. Now there are some more complicated examples which we won't do in this review lesson, but we can maybe touch on them when we talk about the review. All right, so let's go to, okay, so that's higher derivatives, and I also want to talk about the main lesson here today is actually from chapter 3, don't be alarmed, but it's 3.1 and 3.2, and what I want to do is I want to tie in applications of first and second derivatives. Now in our text, really this is in the next chapter, this should be in chapter 2. So the exam that you're going to get is going to get chapter 2 and including 3.1 and 3.2, which you'll find is very, very minor. But I want to draw you a graph here first. So when we have a position versus time graph, all right, so if this is meters, this is seconds, and we have a particle, that's mapped out looking something like this, okay, at this time interval right here, from here to here, the particle has moved from here to here. And so you have, let's say you have this as your first stage. We talked about the instantaneous rate of change being the first derivative. Or if this is a curved function that goes through these points, then the instantaneous rate of change at, let's say, this point right here, we know is the slope of the tangent line. What's the instantaneous rate of change for the change in meters over the change in seconds is going to be meters per second, right? And so the first derivative for a position time graph is the equation for instantaneous speed. And we've talked about this. This is not new. But in 3.1, they formalize it and they explain to you why. And so when you take a look at the position, let's say this is meters above the ground, over time in seconds, the instantaneous rate of change would be the instantaneous velocity or speed. Now, we call it velocity technically because a positive speed and a negative speed has different meaning. So velocity is positive, negative, just like the slope here is positive, and the slope here is negative, right? And so when we're talking about speed, this would be a speed in a certain direction. This would be a speed in the opposite direction. And if this particle is moving, let's say this is distance above the ground, let's say it's moving up, and then it comes to a point where it stops moving up and it starts moving down, you can tell that we have a different direction there. And so that's what the positive and negative aspects mean. They mean something when we're talking about velocity. So let's just summarize that with some notes. Time graph, the first derivative is the instantaneous velocity of the particle. And we've seen that the derivative of the slope would have the units change in y, which is meters, divided by change in time, seconds, meters per second. Okay? Now, my question would be then, and that's no problem. The big thing is, what about the second derivative? Okay? So here's the new issue. And I'll just maybe make that line just a little bit straighter. Okay, so let's say we have a graph where this is speed and this is time. Okay, so this is a different graph, right? This is speed over time. It's not position. Okay, so this right here, this point, does not represent a distance away from anything. This represents a speed. So if this were, okay, so let's say velocity versus time graph, okay? And I had a point right here, 0, 0. That would mean at 0 seconds, this particle is moving at 0 meters per second. Make sense? Okay? Now, let's say this is 1, let's say this is 10. This point right here means the particle is moving at the 1 second mark. It is moving at 10 meters per second. At 2 seconds, the particle is still moving, right? It's moving at 10 meters per second again. And so this is the difference between the velocity time graph and the position time graph, because if you see this on a position time graph, it means the particle is not moving, right? It's stationary. But in this case, what this means is it's got a uniform velocity. So now picks up speed, and then slams on the brakes. Okay? So over time, we may have a graph that looks like this. Okay. And if we are talking about now a derivative of this graph, okay, the derivative of this graph will represent a change in velocity over a change in time. And I should say an instantaneous rate of change of velocity over time. So if we look back at the graph here, excuse me, a derivative, okay, so let's say this is a derivative right here. Right here, that's the derivative at this point right here. What we know about this is that the velocity is changing from 0 to 10 meters per second, right? Because we're at 10 here, we're at 0 here. And so the speed is increasing at this point. The derivative at this point right here is 0. That means the rate of change of the velocity at this point is 0. Remember, the rate of change of the velocity. Now, think about this language. The rate of change of the velocity, rate of change of the velocity, rate of change of the velocity. What word comes to your mind, and if you're in physics, you may have this at the tip of your tongue right now, but what word represents a instantaneous rate of change of velocity? What is that word? Anybody? Okay, let me say it this way. If you are driving in a car and you are speeding up, thank you, acceleration, right, you see? Now, that was easy, right? So think about this. This particle is going from 0 meters per second to 10 meters per second. It is speeding up. So the instantaneous rate of change of velocity with respect to time is called acceleration. The derivative of this graph will represent a change in velocity over a change in time. An instantaneous change of velocity with respect to time. And that, of course, is going to look like this. Let me just draw that for you. And that is going to be meters per second, right? What's meters per second? Well, that is meters per second squared, and that is what we know as acceleration. So an instantaneous change of velocity with respect to time is acceleration. Therefore, the second, this is really important, derivative in a position time graph, not the first derivative, but the second derivative, that's the derivative of the derivative, is acceleration. And you need to have at least 3 or 4 exclamation marks there. I have 5. Because it is pretty exciting. Okay? I mean, I think. It's teacher fun, right? It's teacher exciting. I know it's not the same as kid fun, kid exciting. But anyways, so position time. You see why I type sometimes. Position time graph, okay, here we go. Y prime is instantaneous velocity. Y double prime, that's the second derivative, is instantaneous acceleration. Okay, so just take a moment to just ingest this. Do you have any questions or any thoughts on this? If you are changing positions, right? Position time graph. I am changing positions. I am moving. So I have a velocity. I have a speed in that process. At some point when I am changing positions, I have a speed. First derivative is speed. If my speed is changing, like I'm speeding up, that is, my velocity is constantly changing over time. I am speeding up and it's getting larger. My velocity is getting larger. I am accelerating. That is the instantaneous rate of change of the original rate of change, which is velocity. So acceleration is the derivative of the derivative for position time graph. All right. So if you check your textbook here, you have a graph, and this is on page 128. Now this is said to be a velocity function. Okay. So really, what they mean is we have velocity on this axis right here, and we have time over here. Velocity as a function of time. So there's v, I guess, it's right there, and here's t. All right, so velocity at this point is 0. Velocity at this point is whatever this velocity is, right? But what we're talking about is this. Look at this velocity. Velocity is increasing here, isn't it? Okay. Now, we've got definitely some different curves going here, but let's take a look at this question. The graph of the velocity function is shown. State whether the acceleration is positive, 0, or negative. The velocity is, over time, going up, right? So is this acceleration positive or negative from 0 to A? Over time, speed is increasing, it's positive. Correct. From B to C. Yeah. And you can think of it 2 different ways. The velocity is increasing here, and the derivative of this function is positive. The slope is positive, right? Now let's go back to A to B. Okay, so A to B here, the velocity is, over time, going down. So this is like a deceleration, right? You've heard that word before. Accelerating would be speeding up. Decelerating is slowing down. Or positive acceleration is speeding up. Negative acceleration is slowing down. Good. What about from C to D? Yeah, the velocity is constant, so there is 0 acceleration, right? You're like on cruise control in your car. It's just cruising. The velocity is not changing, and so on. Okay. So I think you guys got that. That's very good. Now, this is a little bit trickier. I want to take a look at this for just a few moments. This is a position time function, so S would be the position, T is time, okay? Position time. Now, at this time right here, the rock or the vehicle or the projectile is here at this position. Over here, At this time, it's at this position. Okay? So for part of the graph 0 to a, the slopes of the tangents can be used to decide whether the velocity is increasing or decreasing, and that is whether the acceleration is positive or negative. So this is going to take a little bit. I just want to introduce this to you to see if you can realize this. So position time, what is the slope of this tangent representing? Velocity, right? It's velocity, yeah. What? I think that's what you said, isn't it? Oh, okay. It is positive, yes. I thought you said velocity, but it's a positive velocity, yes. What about this tangent line right here? If this is a tangent line, that also represents a velocity. Now, how are the velocities changing from 0 to a? That is, how are the slopes changing of these tangent lines? Are the slopes getting larger or are they getting smaller in this little area right here? They are getting larger. So let's say the slope of this line right here, let's say it's about 0.8. And let's say this one, the slope of this line is like 1.5. Okay, you can see that this would be the velocity, meters per second. This is the velocity, let's say meters per second. So between 0 and a, the velocities are increasing. So what does that mean about the acceleration? Acceleration is positive, yes. Okay, acceleration is positive. Now, did everyone get that? Okay, they're getting bigger over time. Now, what about from 0 or A to B? Let's say A to B. Now watch this. If we draw some tangent lines, there's one, there's another one, and there's another one.
This is Kurt. Could you please call
So let's say the slope here is about 2. The slope here is about 1.5, and the slope here is about 0.1. So what can you say about the velocities from A to B? They are getting smaller. So from A to B, what's happening to the acceleration? The acceleration is negative. This particle is slowing down. So from A to B, velocities are decreasing. Therefore, it's negative acceleration, which means that the particle is slowing down. Okay? So you can do a quick work with the tangents here, and I think that's where I'll stop for the lesson today. There are some more obvious things that we can tell about graphs, but I don't want to get too far into it before we have this evaluation. So that's just a little bit about velocities changing and acceleration. Okay, any of you have any questions?